Bismillahirrahmanirrahim. Today we will discuss properties of advanced materials, and under this topic, properties of advanced material, we will discuss optical properties. Assalamu alaikum. Today we are going to discuss the subject inorganic material chemistry. Course code is CAM 3115. Key concept that we will discuss in this lecture is about optical properties of advanced material, and in previous lecture we also discussed about optical properties. We discussed different other about its introduction, optical property about luminescence, and then we discussed a little bit about quantum dots. Then in this lecture we will start from quantum dots and its description, and then we will discuss about applications of quantum dots, and then why this we discussed that the size of particles can change the optical properties. So we will discuss about band structure of materials and the effect of size, that is about quantum confinement effect. As in previous slide, we discussed about quantum dots, that are semiconductor materials which have a size in between 2 to 10 nanometers, and these are mostly spherical nanoparticles. So these are known as quantum dots because in the size is very small, that is between 2 to 10 nanometers. So quantum effect that we will that you can see next in the video, or in that is more prominent. So that's why they are known as quantum dots. And in this figure you can see that you can see different colors of these are solutions of cadmium selenide, and cadmium selenide is a semiconductor, and this composition for this solution is same, and the particles of same material are shown here, but you can see that they are showing different colors, that is that from blue to about orange and red colors. So this and the change in color is due to the different particle sizes. So when these absorb white light and then re-emits, it's couple of nanoseconds later in specific, then they show different colors. So the color depends on the size of nanoparticles, and if we vary the size, then we can change the color of. So these quantum dots are semiconductors, and they are so small that by adding or removing only one electron, it can change the properties, and the color of that material could be changed. So that's why they are the source of light. And the size of quantum dots can we said that size of the quantum dots can change the color that is emitted. So this color change is due to the change in color, change in the size of semiconductor of cadmium selenide. So quantum dots have many applications and that are related to their optical properties. So they could be used in many biomedical applications or many biomedical applications, and these applications may include medical markers. These quantum dots could be used to light up the cancer cells. So in medical, quantum dots have many important applications, like they could be used for cancer treatments, and their big advantage is that they can be targeted at single organs such as liver, are much more precisely than the conventional drugs. So if the where we want to target our drug, then we can use these quantum dots, and that they can light up that cells, and we can check their presence of that cancer cells. So quantum dots are being used in place of organic dyes in biological research, like they can be used like nanoscopic light bulbs to light up and color specific cells that need to be studied under a microscope. So we can use different sizes of quantum dots, and that could be used for to light up that area where we accumulate or where we inject our drug or where we inject uh, uh, material. So we can check the diffusion of uh, that material by lighting up there, by lighting up with different colors. So if we are using different colors of particles, then they will emit different colors, so we can find out that where the drug or where that material is present. So band structure of materials can be represented as, here in this figure you can see that in lower there is a number of atoms, and this arrow is showing increase in energy from down to upward direction. So orbitals based on electron bonding and anti-bonding orbitals in individual atoms. Orbitals from different adjacent atoms overlap, and they can form molecular orbital, different molecular orbitals. For example, in first you can see that there are only two atoms, so two atomic orbitals are will combine and they will form two molecular orbitals, and that there will be there are only two energy levels, and there is a large difference between these two energy levels. So the if there are three atoms then in material, then there will three atoms or atomic orbitals will overlap and they will form three molecular orbitals. Similarly, if there are 14 clusters or 14 atoms in one material, then they will form uh, 14 energy levels. But the difference between these energy levels will decrease as the number of atoms is increased. Similarly, for 20 further energy levels, distance between energy levels will be decreased and an amount of energy levels will be 20. Similarly, for 44 clusters or atoms, the energy levels will be 44. And in case of solids, here you can see that there you cannot see any energy level. So this, for this we say 48. If there are 48 atoms, then they will form uh, a continuous band, and there is no spacing between them. So this is also known as infinite uh, band, or it is also known as continuous band. And similarly, if molecule have a large number of atoms, or that is greater than 40, 48, or it could be 4000 or much than this, then they can form energy bands like this, like continuous energy band. So now when you change the size of particles, you can change the number of atoms in that particle. So what will happen, that instead of having large number of available energy orbitals, you will have a less number of available energy orbitals when you are decreasing the size of particle. When, for example, you are decreasing from micron size to nano size. For example, you have a 100 nanometer size, and when you are going to decreasing the size up to 5 nanometer, you will have very few atoms and very few orbitals. So you will start getting a larger band gap, because the number of available energy levels will become lower. When number of available energy levels is lesser and number of atoms is lesser, then number of energy levels will be less, then there will be larger band gap, and they will separate from each other, and they will separate by larger distance. So the band gap will change, and if band gap changes, then it can the color of by changing the band gap, the color will change. So color which you will see will change in the visible region. So if the light which is there in the visible region varies from, for example, we can say it is 4 micron, there is a wavelength of radiation. So then it shows something like, it will show violet color, and if it is higher and it in higher wavelength, we can say, if we go down in this figure, you can see 0.5 micron or lower energy this scale. This shows energy from overall energy scale is 3.1 electron volt to 1.7 electron volt, which is a kind of visible. This is a visible range of frequency in which we can see different colors. And different. This is here you can see the visible range of frequency and energies. So in this front end scale for in size is 0.5 micron to 7 micron, which shows the colors of visible region, and these are the wavelengths for visible region. So if wavelength of the 0.5 micron or 400 nanometer is around, then it will show violet color, and when it is 500 sizes 500 nanometer, then it will show you green color. And when it is above 600, then it will show orange color. And when it is around 700 or 600 680 nanometers, then you are in the, that could be a 0.7 or 0.6 micron, 0.68 micron or 0.78 micron, then you are in the red color. So different wavelengths have different colors, and wavelength range of visible region of spectrum is from 400 to around 700 nanometers, which is about you can say that it's about zero point 0.4 to zero point 0.7 micron. And the corresponding energy for zero point 0.7 to zero point 0.4 to zero point 0.7 is 3.1 electron volts to 1.7 electron volts, and this whole region is for visible region. So the band gap, this energy is for different band gaps, and if the band gap is 1.7 electron volt, the color you may see is red color, or it might have gone into the lower color, which is red. So if you have uh, if you have a 4.4 micron, and then you go to the lower size, that could be point, suppose it is 0.7375 micron, or it could be 375 nanometer, then you may not see any color. Like we are seeing the range 0.5 micron to 0.7 micron, or it could be 400 nanometer to 700 nanometer, and energy gap is from 3.1 electron volts to 1.7 electron volts. If we go above this region or if we go below this region, then we cannot see the colors. So for example, if we are going to in lower range, that is lower than 0.4 micron, that could be in 0.375 micron, that could be 375 nanometer, then you cannot see any color because it is below the wavelength of visible light. So then you have moved into the ultraviolet radiation. So this is the visible region, and on this side you have the ultraviolet. If you go into lower than 0.4 nanometer, then you can go to UV radiations. And if you are going to higher wavelengths, then it could be you are going to 0.7 to higher wavelength, then you are going to infrared radiation, then you cannot see the colors. So if you you can tune your band gap of material, and if you can tune the band gap, you can tune the colors. You can change the color that you see. So, for example, if you apply an energy that is h nu, which is greater than the band gap or E gap, here in figure you can see, then h nu is greater than E gap, then absorption by electron transition may occur. For example, this is I naught incident beam that strike this any material. Then this lower state red, you can see this is filled states, and the above is unfilled states. And these unfilled states have higher energy, and these filled states have lower energy. And E gap is energy gap between these filled states and unfilled states. And this we are checking for visible region, that is visible region that ranges from 3.1 electron volt to 1.7 electron volt energy band, and its blue, its color range is from blue to red. So, for example, if this I naught incident radiation did fall on this material, then an electron will jump from lower energy filled state to higher energy unfilled states. We can say that they will move from valence band to conduction band. So, if this energy of incidence beam is greater than this band gap, then you will have then this electron can move from valence band to conduction band or from filled state to empty state. For example, if energy gap is less than 1.7 electron volts, then you can have absorption from entire visible region, because the visible region starts from 1.7 to 3.1 electron volts. So if energy gap is less than 1.7, then entire visible can be absorbed and the material looks black or metallic. So if the band gap is smaller than 1.7 electron volt, if the band gap is greater than 3.1 electron volt, then because this 3.1 electron volt is the maximum energy within the visible region. So if you have a band gap which is more than 3 electron volt, then there is no absorption in the visible region, because the visible light is smaller than the 3.1 electron volt, and so you will see material that will be transparent. So if band gap is so you can see the transparent material. So when it is less than 1.7, when it is less than 1.7 electron volt, all the radiations of visible region will be absorbed and material will appear black. So if it is less than 1.7, then material will appear black, and if it is above 3.1 electron volt, then it will low visible absorptions and material will look transparent. And if energy gap is in between these 1.7 and 3.1 electron volt, then you can see different colors ranges that could be from blue, green, orange, red, etc. So the band gap, if different band gap, there is a different band gap, then the color that will appear will be different. So on the basis of band gap, we can observe the color of material, and the band gap is determined by the size of material. Now, other than valence band and conduction band, if you add impurities or dopants, then what happens? You have in this figure you can see that you have a valence band and conduction band, and there is a much difference between both bands. If you add impurity, then you can get some energy levels which are discrete. That means there are not too many impurity atoms. Like you add out of 100%, you add only 1% impurity, so there are not so many impurity atoms, so it cannot form a band. So they are this impurity will work like a energy level, but not too many energy levels in this vicinity, so it cannot form a band. And there are one or two levels maybe there. When we will add impurity, then there will form an energy level, one or two energy level, depending on the amount of impurity that will form between conduction band and valence band. And the energy gap between this conduction band and valence band is much higher. When you will add this impurity, this energy band gap will decrease. So two levels. By adding impurity, there could be one or two levels, and that are two separated by some gap of energy. But if you can design your material such that you choose impurity, you choose a dopant such that you introduce the energy level of impurity in between the conduction band and the valence band, then you can access this energy level. It means that before, the gap between conduction band and valence band is much higher, and for energy to jump that electron from conduction from valence band to conduction band, it needs a lot of energy. Then we can by adding impurity, such kind of impurity that its energy level lies between this conduction band and this valence band, then we can decrease this gap. So we can access this energy level. We have ability to transfer the electron with less energy level. As earlier, we have to transfer electron with higher energy. So when you transfer this impurity level, you need only, for example, in this picture, you can see that in this figure, you can see that this energy level lies between this conduction band and this valence band. So the energy gap between this valence band and this impurity band energy level, that is due to impurity, it is decreased, and this electron can jump from this lower valence state to higher this impurity level. So less energy will be required for the movement of this, for the excitation of this electron. So with lower energy, you can cause an absorption, so that is why sometimes this band gap is very high and you cannot see any color. But so you can, if band gap is very high, then you cannot see any color. So if you add some impurity, then you start seeing some color. That is because you have a transition, which is not in the visible, whereas the band gap is in the ultraviolet. So you can have that by changing the by adding that impurity and by changing the band gap. So actually the colors appear due to the transition of electrons from ground state to excited states, and when they emit some, then they come back to their lower state, then they emit some light and we show colors. So there are different types of absorption now possible. You can have one photon absorption from conduction, like one photon is absorbed from conduction from that valence band to conduction band, and because there one more energy level is added between these two levels, so these photons can come, this emission may come, that electron will come back to first test impurity level, and it can also go to the directly go to the first valence band level. So there will be emission of two kinds of photon, or two or more kinds of photons, or combination of photons that are emitted due to the presence of impurity levels. And how did these impurity levels come? The impurity levels come because you took a solid, and in that solid you have added some impurity atoms. So you can add very small amount of impurity atoms. So for example, if you have 100% solid, then in that you will add 1% impurity, and that 99% will be that your original material. So this so we can take example of here, we can take example of zinc oxide as a host material or original material, and in that you will take 99% of zinc oxide and 1% of europium or terbium or some other species which has energy level in between, which goes right in between or somewhere in between the conduction band and the valence band of host compound. So here host compound is zinc oxide, and the impurity that we are adding is any europium, terbium or some other species. So these there can be these materials can be other host materials, could be oxides of other metals, or it could be chalcogenides, etc. We discussed about size, optical properties, that these change with the change in size. But what is effect of size? Here we will discuss, and it is about quantum size or quantum confinement effect, that is known as quantum confinement effect, when we go from bulk material to quantum dots. So here we can see in the left, we will start from left side, that is bulk material, and this is a 3D bulk solid. And each side, for example, we imagine that for this bulk material, each side is about 10 micron or 10 micrometer, and this is not nanomaterial, this is a bulk material that ranges, all dimensions are in micrometer range. So if we can convert this into a nano size range. If we try to remove one part of this bulk material, we make a thin slices of this 3D bulk material, then we can get two-dimensional material that is known as quantum well, and its two-dimension will be in micrometers range, that is 10 micrometer, but its one dimension will be thin, that will be in nanometer range. So further we will discuss about quantum wire and quantum box, but first, what happens in case of bulk material and in case of quantum well in terms of energy and electrons and its energy. So in bulk energy, in case of bulk material, energy of electron changes as the number uh, density density, and this is called the number of electrons per unit change in energy, or energy difference between E and E plus delta E. So when what is electron density? This is small change in the energy. So it is plotted here, that is called rho. It is plotted on the x-axis and energy is plotted on the y-axis. Rho is about also called density of states or the density of energy state. That means how many levels are closely packed. That is density is higher or low, it varies with energy. So this lower density arrow tells us about the energy state, that how closely these are packed, and it varies with energy. So if you see for bulk object, the row of energy or density varies in this manner, that it looks like a parabola. So when the density is 0 and the rho, when the density is 0 and the rho is 0, so at the zero energy level, at zero energy, it changes and goes up, and density increases till a certain value of energy, and after that lines stops, and that means that there are no states above this value, and this at which this is final state. This is called Fermi level. As in previous slides, in band gaps of materials, here we can see for bulk material, this energy states will be closely packed, and these will be continuous. And when we decrease the size and there will be less number of atoms, then the band gap will increase, and the energy levels, the energy between different energy levels will increase, and their states will be energy levels and their energy density of energy atoms will decrease. So first, if we start from left side of the figure, first we talk about bulk material, and this first shows the density of states plot for a bulk material which has got 3 dimension in micrometer. Now, when the size decreases, like if we cut that bulk material into pieces, and we make prepare two-dimensional structure, and that is known as quantum well, then we are talking about quantum confinement or quantum size effect. So when size decreases from bulk, and if we talk about quantum well, because the properties of electrons and its energy levels are going to be affected by changing the size. So how they are going to be affected? The shape of this curve, in case of quantum well, you can see that the shape of this curve now has step-like feature. So in a quantum well, you have one dimension very small. So you can say it is nanomaterial because one of the dimension is in nanometer range or in nano size. So we can say this is nanomaterial, and other two dimensions are not nano sized. So in case of quantum well, one dimension will be in nano scale and other will be not in nano range. So this because one dimension is in nano sized or in nanometer range, then we can say this is nanomaterial. And this quantum well we are considering is at a two-dimensional structure, so it is plate-like structure. So when this happens, when it is nano one dimension is nanometer range, the density of state is in stepwise manner. So it does not vary continuously like in bulk solid. The density of state was continuously changed, and it at the end it only will get constant value. But in case of quantum well, we cannot get continuous. It will not vary continuously. So you have density of state from in this figure you can see that the density of states are not starting from zero like in case of bulk. So from certain energy level, then you get that energy density of states, and below that there is low density of state. Below that certain energy level there is low energy density of states. So that means electron cannot have energy of this value at that state, only it can have energy above this value. So it is starting from above zero value. So till this value you have a certain density of states. When you go to high energy, you have high density of states. So here you can see that plot, and there are three steps in case of quantum well: first step, second step, and third step. So if you see the right side, the density of state is increasing as you are increasing it, as energy is going to be increased. So and for each step the density of states is constant. So in case of quantum where we say that density of state is constant at the for each step. So this is called quantum confinement effect, because in bulk density of state is not constant at all for any energy. In case of bulk, it changes continuously, whereas in case of quantum well, density of states are constant over a constant energy range, and then it suddenly changes and again become constant for another energy level. So here you can see the first step, it suddenly changes and then it becomes constant at the end of that step, and then again it suddenly rises, it changes suddenly, and then it becomes constant for the second at the end of second step, and the same happens for the other steps. So this happens for the quantum well, where one dimension is nano sized, or where one dimension is nano in nanometer range. Now we will talk about quantum wire. And quantum wire where two dimensions are nano sized, and and one dimension is still long, that we call it is quantum wire. This is one dimensional structure, and and we can call it quantum wire. The nature of this density of state diagram again will change for quantum wire. It will be different from quantum well and pulse material. So in case of quantum well, so there is in case of quantum wire there is a variation uh, in the density of state in this region. And in first step you can see that there is variation and in the density of states in first region, and then suddenly it jumps to another density of states, and then again there is a small variation. But in case of quantum well, it was it was a constant variation. It was constant. So this plot of density of state versus energy is very characteristic in case of quantum wire, whether you have a bulk particle, whether you have a well-like structure, so a quantum well-like structure. So these density of states are very plots for the density of states are characteristics are they are particular for every kind of structure. So in case of quantum wire, the one dimension is long, that could be micrometer. It's not in the nanometer range, but other dimensions are very small, and we can get this plot like we get in three steps that are varying suddenly. So if we further reduce this size and we say that reduce this nano size in all three dimensions, and here 1, 2, and 3, all three dimensions are in nano size range, then we can also say it as quantum box, or it is also known as quantum dot. So it will be like a nanoparticle, like all three dimensions are here are confined, and they are very small, that are all in nano size range. So why here we say it quantum confinement or quantum size effect? Because electrons are not here in case of three-dimensional structure when size is very small, and all three sizes are in nanometer range. Then in this case, electrons are not allowed to move outside this box. So the dimension is so small, because electrons cannot go out of these particles, and they will strike again and again in that particle, and the properties of that material will change. So the electron has to be within, and so electron cannot go outside. The electron has to be within that nanoparticle inside that quantum box. So if you think about its atomic structure, the energy levels are now, in this case, in case of quantum box or in case of quantum dot, the energy levels are not discrete. You can see there is some gaps between them, and they are straight lines. So like in this case, the density of states, density of states for a particular energy is varying, but in case of a quantum box, the density of states cannot change with energy continuity, or even in small band it changes drastically. So if you have discrete energy level, for example, one is if you say that this first level is energy E1 and the second level is E2, so the energy of states, density of states at E1, and then there will be another energy E2. Then here you can have some density of states, but between E1 and E2 energy states, you don't have any density of states. So this is quantum box, and here you can get discrete energy levels, and then the properties here you will get, optical properties you will get, that will be different from and the other quantum wires, quantum well, or bulk materials. So here we took the example of four materials, that one is a bulk material, and other we talk about we discuss the plot of quantum well and its states of energy, states of density of states. Quantum well is two-dimensional structure. Then we talk about quantum wire and about its plot. It is one-dimensional structure where one dimension is out of nanometer range. And then we talk about quantum box or quantum dot, that in which all three dimensions are in nanometer range. So overall, we talk about these energy levels and variation in the nature of the density of states versus energy plot, which cause all the changes in optical properties of the system. Because what will happen to electrons when they are absorbed or moved from lower energy level to higher energy level? It will be very different from a shining light and pushing electrons between these levels. and again when it will come back, that the phenomena will be different. So in all these cases, because the energy level diagram is different for all these four structures that we mentioned here, the energy level diagram is different because of the type or size of the particle, and the shape of the particle can also affect it. So hence the optical properties will be different.